Greetings and salutations, magical chemists. Today we're going to review the basics of equilibrium. Now, equilibrium is a state that all chemical systems are trying to reach. It's their most stable place. You'll know that you've reached a state of dynamic equilibrium because at that point in time, the concentration of all reactants and products will remain constant. This happens because at equilibrium, the reaction is proceeding in both the forward and reverse directions simultaneously at the same rate. This means that all macroscopic variables you could measure, like concentration, partial pressure, temperature, do not change, so nothing appears to be happening. You'll also know you're at equilibrium because your reaction quotient, Q, will be equal to K, the equilibrium constant. It is essential to remember that the position of equilibrium is temperature dependent. That means if you change the temperature, you're going to change the ratio of products to reactants at equilibrium. We can, of course, calculate the value of the equilibrium constant K by plugging into the equilibrium constant expression, which is basically taking the concentration of each product raised to the stoichiometric coefficient divided by the concentration of each reactant raised to its stoichiometric coefficient. However, please remember to only use gaseous and aqueous substances when you're plugging into the equilibrium constant expression. This is because solids and pure liquids have a constant concentration. Also, quick reminder, there are no units for the equilibrium constant K. All right, let's try some practice problems to see what you remember. Technically, you already have learned how to do both of these problems back in Unit 2, so you are welcome to try them on your own, or if you'd like, I'll walk through the first one with you together. In the first problem, we're looking at the decomposition of aqueous calcium hydrogen carbonate, and they've given you equilibrium concentrations of some of the things being produced, and they would like you to calculate the value of the equilibrium constant K. Well, if you want to solve for K, first you need to write out the equilibrium constant expression. That's just a fancy way of saying write the ratio of products to reactants. And there you have it. You might be thinking, wait, but you left out like more than half of the products. Yeah, I did, but there's the reason. Did you notice that the calcium carbonate produced is a solid? The delicious water produced is a liquid. They are not included in your equilibrium constant expression. Only the things that are aqueous or gas. Once we've written that, it's easy enough to plug in the values given and solve for K. Since we are dividing, and one of the things we're dividing by only has 2 sig figs, that means our final answer will also only have 2 sig figs. And so we've calculated K equal to 110. Well, if the ratio of products to reactants is 110, we've got about 100 times more products than reactants at equilibrium. You may or may not remember, but we call this product favored. All right, if you didn't try any of these on your own yet, you should totally try number 2. And when you're ready to check, unpause the video. For this problem, if you start plugging in the given concentrations, you'll notice you're missing one. And in fact, that's what they're asking you to solve for. But luckily, they also gave us the value of Kc. So this just becomes delicious algebra. Once you've rearranged to solve for the concentration of carbon dioxide, you get 1.10 molar, keeping 3 sig figs. And notice, we do have a unit this time because we're solving for concentration. We weren't solving for K. Okay, so that's the math behind K. But what does K actually mean? A good question, right? Well, the equilibrium constant K tells you the ratio of products to reactants when a given reaction reaches its lowest free energy state and, quote unquote, stops. We know it doesn't really stop because it's in dynamic equilibrium and reactants are turning to products and back and forth, but it appears to stop, so that works for us. We can actually make an analogy between gravitational potential energy and chemical potential energy by graphing Gibbs free energy versus the ratio of products to reactants. Just like balls rolling down a hill, your chemical system is going to react until it reaches its most stable point. And that's what will come to a, well, quote unquote, stop. This is the point in time where the ratio of products to reactants is exactly equal to K, the equilibrium constant. But of course, your chemical system isn't always at equilibrium. If the chemical system is actually running, it's because your system is somewhere else on this diagram. If the equilibrium or most stable ratio of products to reactants has more products than you have under current conditions, well, your chemical reaction is driven to roll down to the bottom of the hill. It's driven towards the product side. However, if you have too many products at your current conditions, then the reaction is going to be driven to run backwards until it reaches equilibrium. But in all cases, your chemical system is going to react until it has reached its lowest free energy state, and that is equilibrium. The thing about equilibrium is the location of that most stable point is different for every different chemical system. So you can have a reaction that is very product favored. That means your ratio of product to reactants, or K, is greater than 1. That means that in your free energy diagram for this product favored reaction, your equilibrium point is going to be at a really high ratio of products to reactants. Well, it can be the other way around too. If the most stable point for a chemical system generally favors reactants, your K value is less than 1, well, this time your free energy diagram is going to show its lowest point, its point of stability, much closer to being pure reactants. And of course, if K is about equal to 1, it's about half and half. That's why it's essential for every given chemical system to make sure you know the value of K for that system. That's how we can predict where a reaction will reach its point of stability. Now, technically speaking, some reactions aren't equilibrium reactions at all. Some reactions actually go to completion. Well, if you recall, completion reactions, where it's just basically reactants go to products and they don't go back, we show that with a one-way arrow. The equilibrium reactions, where they can go in both ways, we show with a double-sided arrow. But you can still look at this free energy diagram as an analogy, because in a completion reaction, it's basically a one-way slope. You're rolling downhill no matter where the chemical system is. If it's not 100% products, that's where it's going to go. That's a completion reaction, and they are non-reversible. You can't go back. Combustion is a classic example. You can't unburn something. Equilibrium reactions, of course, as the double-sided arrow suggests, are reversible, which means the reaction is going to occur until the lowest energy state is reached, and then, who are we kidding? The reaction's still happening, just at equal rates in both directions. So a weak acid dissolution is a classic example. A weak acid will only partially dissolve. So to have a kind of conceptual understanding of K, it can be helpful to think of K as a measurement of how close a reaction goes to 100% completion. If you have a high value of K, the reaction came pretty close to completely turning reactants into products. But low value of K, not so much. The reaction doesn't come close. In fact, the reactants are just mostly hanging around. Now, there is an interesting intersection between equilibrium and kinetics that I think would be awesome to talk about here. There is a situation called kinetic control, and that is when a reaction is thermodynamically favorable. Basically, if you look at its free energy diagram, it's much more favored, like the reactants are the products are much more favored. But the products are forming so slowly that it appears the reaction isn't actually happening. Basically, it is a reaction that is thermodynamically favorable, but kinetically unfavorable. I see questions like this show up, scattered among just every once in a while among the multiple choice or the free response in the AP Chem test. So let's take a look at this one. It says for a given reaction of A converting to B, it's an equilibrium reaction, well, they give you a delta H value that's negative, and they give you a delta S value that's positive. Change in enthalpy, change in entropy. And a student tries the reaction and lets the reaction run over time, but after 2 days, she measures the composition and discovers that it is primarily reactants. What can we conclude? let's remind ourselves how thermodynamics work. Because if you have a negative delta H, that's exothermic, and a positive delta S, that's increasing entropy, this reaction is driven by both entropy and enthalpy. Under these conditions, this reaction is always thermodynamically favored. That means K is greater than 1 regardless of temperature conditions. So if you notice, they're trying to trick you in a lot of these answer choices. Well, this reaction is only thermodynamically favorable at low temperatures, or it's only thermodynamically favorable at high temperatures. Nope and nope. Hopefully you remember, things are only thermodynamically favored at low temperatures if both are negative. Only thermodynamically favored at high temperatures if both are positive. We also know it's not going to have a small equilibrium constant, so it can't be B, because K has to be greater than 1. It's a negative delta G. It's thermodynamically favored. Well, hopefully that means C is the right answer because we've narrowed down everything else. And indeed, it is describing kinetic control. The reaction has an extremely high activation energy, right? It's a really high energy bump to get over, and so it's going to be really, really slow. Okay, let's go back to that equilibrium constant K. It turns out we can put a lot of random subscripts on K. It's kind of like with delta H. But the subscripts kind of just tell us about the reaction being studied. They're all still the same ratio of products to reactants. The generic K expression is the one we've been using. And sometimes they say KEQ or KC. So like K equilibrium or K concentration. And that looks, just like we've been doing, the ratio of concentrations. But you can also write Kp, which is the ratio of products to reactants for partial pressures. Please notice partial pressures are written as a capital P with a subscript of the chemical. So there are no square brackets in a Kp expression. There's even something called Ksp. It's the solubility product constant. It's basically the equilibrium constant when you're dissolving stuff. And we're going to look at that one before the end of this unit. Now, because Kp and Kc are basically the same equation, the same ratio, but one's partial pressures and one's concentration, we're going to do a lot of mixed problems where you're just jumping between one to the other. Now, it shouldn't surprise you that Kp is only useful if you're doing reactions that are, gaseous. And what's interesting is you actually can convert the Kc into Kp, like the ratio in concentration relative to the ratio in pressure. But it turns out that's not AP tested anymore, so you don't have to worry about it. So let's go ahead and try just a couple of practice problems with Kp so you can see what this equilibrium math looks like when you're working with partial pressure instead of concentration. Okay, you are more than welcome to jump in and do these on your own because honestly, it is really the same thing mathematically. But watch out for the way you're writing things. So if you want to be sure you're setting up Kp correctly, let's go ahead and try the first one together. You'll notice the process is very similar. They give you a K value, they give you a reaction, they give you this time equilibrium partial pressures. And hey, look at that. They want you to calculate the equilibrium partial pressure of no. We're just going to plug into the Kp expression and solve, just like we did earlier in the Kc expression. But let's watch out for that Kp expression. Okay, there's Kp. Notice it's still products over reactants. You're still using those stoichiometric coefficients, so you had to square two of those chemicals. But there are parentheses, no square brackets. But now all we need to do, plug in the numbers we know, solve for the one we don't. Yay, math. When you get your final answer, it will of course be in atmospheres because you just solved for a partial pressure. All right, if you haven't yet, try the second one, and when you're ready to check, unpause the video. The second problem was just plugging into the expression to solve for Kp. That's it. So there you have it. Thank you for playing with the glories of chemistry.